All right. For our chapter 3.4 notes, we're going to learn about concavity and the second derivative test. We talked about concavity a lot in AP Pre-Calc. Okay, so remember what we've been doing. We can determine where any function or anything really is increasing or decreasing based on the first derivative, right? We find the critical numbers because critical numbers are where functions can change from increasing to decreasing. And we use the first derivative test to figure out whether the function is increasing or decreasing. Today, we're looking at the second derivative and where the second derivative is positive and negative, and that's going to help us determine where the first derivative is increasing or decreasing, which is related to concavity. So by looking at the sign, the plus or minus sign of the second derivative, it means that we're looking for where the first derivative is increasing or decreasing. And remember, we looked at this a lot last year. Is the rate of change increasing or decreasing? The first derivative increasing determines where the function is concave up. Remember, that looks like this. Or where the function is concave down. So I'm hoping that this is a review, if you had AP Pre-Calc last year, about how can we relate rates of change with concavity. Okay, so concavity, f has to be differentiable on the interval that we're looking at. Open interval just doesn't include endpoints. The graph of f is concave up if f prime is increasing. So remember, the words kind of go together. Concave up if f prime is increasing, and concave down if f prime is decreasing. Make sure that you're avoiding the word it when you're justifying these. It's not it's concave up because it is increasing. You wouldn't get any points for that. It has to be f is concave up because f prime is increasing. So here it is in pictures. These slopes are increasing. If we were to list out, let's approximate numbers for slopes because that's what derivatives are. We start at 0, and then maybe the slope is like 1/3, and then maybe it bumps up to 1/2, and now maybe it's up here at like 2. So those slope numbers are increasing, and that makes the graph concave up. So the graph is sitting above the tangent lines. If you take a look at that, our graph is higher than what the tangent line might approximate. And we also can see that f prime is increasing. And we also can see that that means the second derivative, if a function is increasing, the derivative of that function is positive. So here's an example of a concave up function. We know x squared is concave up. We know its derivative is 2x. That is an increasing function. And we know that 2 is a positive number. Okay, so a concave down section. When you have a graph that's concave down, these tangent lines are now sitting above the graph. Like if I drew the tangent line, the piece of the line that's outside of the graph is above. So now the graph itself of f is below the tangent lines. And if we were to look at these slopes, maybe this one is positive 1/2, and then we hit 0, and then maybe we hit negative 1/2, and now maybe the slope's -1. So these slope numbers are decreasing. So f prime is decreasing. And the derivative of something that's decreasing, so f double prime in this case, would then have to be negative. All right. To find the open intervals where the graph is concave up or concave down, we need to know if f prime is increasing or decreasing. And how do we know when something increases or decreases? We talked about this in the last set of notes. Anytime I want to know if something, it doesn't matter what the function is increasing or decreasing, I look at its derivative. I guess there's no apostrophe there. Look at its derivative to see plus or minus. If something is increasing, its derivative will be positive. If something is decreasing, its derivative will be negative. So test for concavity. So this is not the second derivative test. This is just how do we test for concavity? We find f double prime, second derivative. If f double prime is positive, then f is concave up. If f double prime is negative, f is concave down. And if f double prime is 0, that could be that there's no concavity. because f is linear. That would be like if it's on an entire interval, right? So to apply this test, you need to find the possible inflection points. We abbreviate those as pips. Find the pips, possible inflection points, kind of like critical numbers, but for the second derivative. And those occur where f double prime equals 0 or where f double prime is undefined. And then we need to put those pips on a number line and test intervals. Or if you know what the f double prime graph looks like if it's polynomial or linear or something, you can sketch the graph. And then you draw your conclusion about concave up or concave down. If f double prime, oops, not triple prime, if f double prime changes signs, so it doesn't matter, positive to negative, negative to positive, whatever. If f double prime changes signs, then the pip is now a point of inflection. And again, we learned about points of inflection in AP Pre-Calc last year. We can abbreviate that POI. A point of inflection is where a graph changes concavity. So if f double prime changes signs, it really means that f changes concavity. All right, so what we're doing here is determining the open interval on which the graph is concave up or concave down. Identify points of inflection. All right, so here's the original y. So let's find y prime, or dy dx. That would be negative 3x squared plus 6x minus 2 becomes 0. Now we find the second derivative, y double prime, or derivative of, you could use this notation, d squared y over dx squared. That would be negative 6x plus 6. Find our pips, our possible inflection points, by setting the second derivative equal to 0. There's no place where this would be undefined. If I add 6x and divide by 6, I would then get x equals 1. So 1 is a possible inflection point. So now we need to come over here to a number line and place it on the number line. And just like we did with the first derivative test, plug values or sketch the graph of y double prime. Plug that in to see whether the second derivative is positive or negative. All right, so now I could just sketch this graph. And our homework tonight has a lot of linear derivatives, so second derivatives. So I could say, okay, negative 6x plus 6 is a line that looks like this. Its x-intercept is 0, apparently. So it's definitely positive to the left and negative to the right. And that means that y is concave up on the left and concave down on the right. It means that y prime is increasing and then decreasing. So the question is concave up or concave down. Remember, just like first derivative test, none of this counts for your AP grader. They will not consider any of this, whether you've done it correctly or not. So you do need to answer that we have, let's see, so y is, I'm going to abbreviate, but you would write out the words, concave up on negative infinity to 1 because y double prime is greater than 0. Y is concave down on 1 to infinity because y double prime is less than 0. Get in the habit of practicing writing this out. I said this for first derivative test. Write all of this out because you're going to have to justify on my test, on the AP test, and that way it'll just be natural. We also were supposed to identify a point of inflection. So there is a point of inflection at 1 because the second derivative changed signs. So I'm going to find what y of 1 is over here. So plug 1 back into y's equation, you get negative 1 plus 3 minus 2. That's 2 minus 2, which is 0. So the point 0, 1 is a point of inflection. And again, justify because y double prime, you just have to say changed signs. It's not like first derivative test. We're not saying max or min. We don't have to specify positive to negative. It's just, oh yeah, the changed signs, that means y changed concavity. All right, so that is this answer. Okay, let's do this again. You can use quotient rule here, or I'm going to rewrite f of x, I think. Anytime the numerator is just a number, I kind of like doing it this way, but you don't have to. I like product rule. or I'm sorry, power rule, but you could do quotient rule if you want to. So let's find f prime of x. So that's going to be negative 6 times x squared plus 3 to the negative 2. And then remember to chain rule. The derivative of x squared plus 3 is 2x. All right, let's clean that up a bit before we take the derivative again. I'm going to leave it with its negative exponent here. So it's negative 12x times x squared plus 3 to the negative 2. Okay, so now I need to take the derivative of this. So the second derivative, power rule again, this would become positive 24x. X squared plus 3 is now to the negative third power. And remember to chain rule again, the derivative of x squared plus 3 is 2x. And I'm going to clean it up so that it makes, so that I can more easily find places where f double prime is equal to 0 or undefined. So I'm combining my numerator a bit and cleaning up my denominator, or getting my, getting rid of my negative exponent to clean up the denominator. All right, so pips. F double prime is equal to 0 at x equals 0, and f double prime is undefined when x squared plus 3 cubed equals 0. Now here, think about x squared plus 3. That's never negative, right? Squaring something is positive, adding 3 keeps it positive. Or if you start trying to solve for this, you would get something imaginary. So there are no real number pips that we can get from that. But we do have x equals 0. Okay, so now we're going to come over to our, oh shoot, you know what? Gosh, I made a big mistake here. Okay, sorry, I can erase more easily than you. What was my big, huge mistake? Well, I was fine with the first derivative. I knew I missed something because I didn't have as complicated of a problem as I thought I should. First derivative was totally fine, right? It was negative 6 x squared plus 3 to the negative 2. Chain rule. This was totally fine. What did I mess up back here when I took the second derivative? All right, so I'm going to leave this in the video because it's a good reminder. So I just started taking derivatives and multiplying them together, and that was silly of me because this requires a product rule, right? Product of two functions. First time it was just a constant, so I didn't have to do product rule, but now it's a product rule for sure. Okay, let's try this again. First times derivative of the second. So derivative of the second part will be negative 2 x squared plus 3 to the negative 3 times 2x plus second times derivative of the first. Has a bit more to it, right? Now, product rule does mean that you're going to have to factor stuff out. So if factoring is not quite your thing, you might want to have rewritten f prime and done quotient rule instead. But I'm going to clean this up first. So negative 12x times negative 2 is positive 24x times 2x is positive 48x squared. And then there's this x squared plus 3 to the negative third. And then let's just make this minus 12, x squared plus 3 to the negative 2. So the reason I want to factor out a GCF is because, remember, we're trying to set f double prime equal to 0 and see where it's undefined. So we want to get rid of negative exponents, and we want this to be one fraction. So I can factor out a 12, and I can factor out an x squared plus 3. I'm going to leave room. An x squared plus 3 to the negative 3, because remember, an exponent of negative 3 is lower than an exponent of negative 2. So when you factor that out, if it helps you, show what you're doing. You are dividing each term by that GCF that you just factored out. Even though it takes time to write that out, it can be helpful and save mistakes. So 48 over 12 is 4. The x squared is still there, but the x squared plus 3 to the negative third divides out to 1. Here, the 12s divide out. There is a minus. And then I would still have parentheses, x squared plus 3 to the first power, because negative 2 minus negative 3 is 1. All right, so now this 12 stays up here. x squared plus 3 to the negative third gets sent to the denominator. Now it's to the positive third. 4x squared minus x squared is 3x squared, and distribute the negative all the way through, so it should be minus 3. All right, so that gives me some more values, right? So when we do our pips, we get x squared could equal 3 divided by 3, could equal 1. So x could be plus or minus 1. And what I was saying before I realized my mistake, x squared plus 3 could equal 0, except it can't. It's always positive. So if you start solving and you get an imaginary, it just means there are no real number possible inflection points there. So plus and minus 1 are the only candidates. Put them on a number line. Now this is the graph of f, by the way. So we can see that these are going to be inflection points, but let's just connect it to our graph here. So f double prime. So this one, I'm not going to sketch this graph. This is much more difficult for me to sketch. So I'm going to plug numbers in. If I plug in negative 2, I get 12 times 3 times 4 is 12 minus 3 over, remember, x squared plus 3 is always positive, and then you're cubing it. Doesn't matter what you plug in. So you don't have to spend a ton of time crunching numbers. You're just saying, what does this come out to? A positive on top over a positive on the bottom, so positive overall. And then something between negative 1 and 1 would be 0. So that would be 12 times 0 minus 3 over, again, always positive, cubed. That's a negative over a positive, so that whole section should be negative. And if I plug in positive 2, I get 12 times 3 times 4, 12 minus 3 again, over this always positive. So same thing that happened with negative 2, I get a positive. So this means that f double prime changed signs at plus or minus 1. So there are points of inflection. We should go ahead and find what is f of plus or minus 1. F is 6 over x squared plus 3. So whether I plug in plus or minus 1, I do get the same answer. So it's 6 over 1 plus 3. 6 over 4 is 3 over 2. All right, so I have enough information to answer the question here. So the question was concavity and points of inflection. So I'm going to say f of x is concave up on negative infinity to negative 1 and 1 to infinity because f double prime of x is greater than 0. F of x is concave down on negative 1 to 1 because f double prime of x is less than 0. And plus or minus 1, 3 over 2, is a point of inflection because f double prime changed signs. You don't have to get into plus to minus, minus to plus. Just change signs. All right. Let's do let's look at the next page here. So, okay, remember we had first derivative test, and that helped us find relative extrema, relative max and mins, because first derivative test helps us determine where a function is increasing and decreasing. Today, the second derivative test is something that can still help us draw that same conclusion, find a relative max and min, but instead of basing it off of where is the function changing from increasing to decreasing, we're looking at where does the function have a horizontal tangent and what's the concavity? Because if you have a horizontal tangent, I have it down here. If you have a horizontal tangent and you've got a function that's concave up, you've got a relative min. If you have a horizontal tangent and a function is concave down, that's a relative max. Okay, so I honestly, though, I don't use second derivative test all that often because sometimes it's inconclusive. So when finding a relative max or min, you always find the critical numbers. So you're always going to set the first derivative equal to 0. And then sometimes you have a choice. You could say, I'm going to carry on with first derivative test, or sometimes it might be nice to carry on with second derivative test. So, okay, so here we go. At x1, f prime of x1 would equal 0, right? So x1 is a critical number. And then if I plug in the second derivative at x1, because the graph is concave up at x1 and everywhere else on this little section, I know that that would be greater than 0. So if I get a critical number and I plug that critical number in and get a positive second derivative, then that means that f has a relative min at x1. And if I can show that there's a horizontal tangent at x2, that means that, again, f prime of x2 should be coming out to 0. So there is a critical number at x2. Okay, and if I plug x2 into the second derivative, because the graph is concave down here, I should be finding that the second derivative is negative. And again, this is assuming you're not actually looking at the graph. So that would mean that f has a relative max at x2. So the third case is like, what if I get a critical number at x3, which means that f prime of x3 came out to 0. And what if the second derivative is not positive or negative, but it's equal to 0? Then this second derivative test is inconclusive. I'm just going to say it fails. That means that we have to go back and do the first derivative test. So the reason I don't usually use the second derivative test by choice is I don't want to go through the trouble of finding the second derivative and plugging stuff in, and then I just get an inconclusive test and I have to go back and do first derivative test anyway. So the only time I use this is if they prompt me to in the AP question. Sometimes they will have you go through these steps in a couple of different parts. Okay, apply the test. So first step is find critical numbers, which is where f prime of x is equal to 0. Or I guess undefined, but that's, if f prime is undefined, then f double prime will be undefined. So just where f prime is equal to 0. And then we're going to find f double prime of x. And then we're going to evaluate f double prime of x at the critical numbers and draw our conclusion. Okay, so find all relative extrema, use the second derivative test. All right, so f prime that becomes 0. It's 6x minus 3x squared. Find the critical numbers. So when is this equal to 0? Well, I can factor out a 3x. That leaves me with 2 minus x. I get 0 and 2. So those are the critical numbers. Now, first derivative test is put them on a number line and test. Second derivative test says now find f double prime of x. So that would be 6 minus 6x. Evaluate f double prime at each of these values. So at 0, I would get 6. And f double prime evaluated at 2, I would get 6 minus 12, so negative 6. So because I didn't get 0, I can make a conclusion here. So 6 is greater than 0, and negative 6 is less than 0. So at 0, the graph is concave up, so that means we have a relative min. And at 2, because I got a negative derivative, second derivative, it means the graph is concave down at that point, and there's a relative max. So my reasoning here, I should find the values. So my reasoning here, I'll justify in a second. Let's go ahead and find the values. What is f of 0 then? Plug 0 into f, you get 5. And what is f of 2? That's 5 plus 3 times 4 minus 2 squared. 17 minus 8 is 9. Okay, so the point 0, 5 is a relative, I always need the picture, relative min, because f prime of 0 equals 0 and f double prime of 0 is greater than 0. That's your justification. And then 2, 9 is a relative max because f prime of 2 is equal to 0 and f double prime of 2 was less than 0. You don't have to get into spelling out concavity and all of that stuff. This is how you justify. Okay, let's look at example 2. So example 2 here, let's find f prime. So this becomes 4 times 1/4 is 1. So this is just x to the third minus 8. Find the critical numbers. Now, remember, we've done a million speed quizzes and we factor all of this, but we don't solve these on the speed quiz. So you might need reminding here. You get x equals 2. This always gives you imaginary solutions, or complex, I should say. But you do not need to bother doing quadratic formula. This does not factor. You would get imaginaries. So we get 2 here. So now let's find f double prime. That would be 3x squared. And let's evaluate f double prime at 2. 3 times 4 is 12, which is greater than 0. Again, I have to sketch this out. If the second derivative is positive, concave up, so I've got a relative min. So let's see. What is f of 2? F of 2 is 1/4 times 16 minus 16. This is 4 minus 16. It's negative 12. So the point 2, negative 12 is a relative min because f prime of 2 equals 0. That's a critical number. And the second derivative at 2 was greater than 0. All right. Let's look at number 3. So f prime of x is negative 15x to the fourth plus 15x squared. Find your critical numbers. So factor out, I'm going to factor out a negative 15x squared. That makes this x positive x squared minus 1. So the critical numbers are 0 and plus or minus 1. And then we find the second derivative. So the nice thing about this second derivative test, I guess, is kind of nice here because I don't have to put 3 sections on a number line, but I don't know. Okay, so if I do this, I get negative 60x to the third plus 30x. So evaluate at 0, and you get 0, so that's inconclusive. So that's annoying. I do have to do the first derivative test for that one. Now, if I plug in plus or minus 1, I will get solutions there. So I could still do this. Plug in 1, and you get negative 60 plus 30. That's less than 0. And plug in negative 1, and you get positive 60 minus 30. That's greater than 0. So I can make conclusions about these. We're concave down and concave up. But I still need to evaluate the first derivative, at least on either side of 0. And I have to be careful because I can't go plugging in negative 1 and 1. I've got to plug in like negative 1/2. So I can either plug in negative 1/2 and positive 1/2 into f prime, or remember, f prime is polynomial, so you can use your skills about like, oh yeah, this graph goes down on each side, it crosses through or changes signs at negative 1, but it touches and turns at 0, or bounce was our informal way to say that. So the first derivative is negative and then positive and then positive and then negative. So there is no sign change, or the first derivative, there's no changing behavior for the graph. So there is no relative extrema at 0. The graph of f goes from decreasing to increasing to still increasing to decreasing. All right, so there's nothing at 0. What is f of 1? It's negative 3 plus 5, so it's 2. What is f of negative 1? Positive 3 minus 5, so it's negative 2. So the point 1, 2 is a relative max because f prime of 1 equals 0 and f double prime of 1 was less than 0. And then the point negative 1, negative 2 is a relative min because f prime of negative 1 is equal to 0 and f double prime of negative 1 is greater than 0. And there is no point of inflection there is no relative extrema at 0 because f prime did not change signs. Okay, example 4, this is our last example here. So taking a look at this, to find g prime, now I don't want to mess this up again. I need to do product rule right off the bat. Okay, so first times derivative of the second, that's going to be 3 times 2 minus x squared. What's the derivative of 2 minus x? Be careful here, it's minus 1, so don't overlook that. Plus the second times the derivative of the first, which is just 1. So let's clean this up. So this is like negative 3x times 2 minus x squared plus 2 minus x to the third. Okay, and then we need to find the critical numbers. So when is this thing equal to 0? So let's factor out a 2 minus x squared. That would leave you with negative 3x. Sorry, I got to recharge my pen. Okay, that would leave you with negative 3x plus 2 minus x to the first. 2 minus x squared, and then this is negative 3x minus x is negative 4x plus 2. So x could be 2, or x could be 1/2. Those are critical numbers. Now, here's the thing about second derivative test. Do you really want to do the second derivative test? Do you want to take the derivative of this, which needs a product rule and another chain rule here, and then work on that? Or do you just want to do the work of first derivative test? I would just do first derivative test, unless I'm really forced to do second derivative. So at this point, I'm just going to use first derivative test. Because imagine going through all the work and then maybe second derivative is inconclusive. Like, no, if the second derivative is too hard is going to be cumbersome to find, I should say, then I'm not going to bother finding it. Okay, so first derivative test. This is from the previous set of notes. Now, I don't want to sketch the graph of g prime. I guess I could. I have it simplified here, but let's just test numbers. Plug in 0 into g prime. You would get 0 for the first term, plus 2 to the third. That's positive. What's between 1/2 and 2? 1. So you'd get negative 3 times 1 squared plus 1 to the third. So that's negative 2. So that's negative. And put in something like 3. Negative 3 times 3 times, negative 3 times, let's see. We're going into negative 3x. Yeah, negative 3 times 3. 2 minus 1 is negative 1, but we square it. Okay, and then that's going to be plus 2 minus 3 is negative 1 to the third. So negative 3 minus 1 is negative 4. So negative here. So that tells me that g is increasing and then decreasing. So the only relative extrema where we go from increasing to decreasing is at 1/2. Right? So we find g of 1/2. It's 1/2 times 2 minus 1/2. So 2 minus 1/2 is 3 over 2 to the third. That's going to be 27 over 8 times 2, 27 over 16. So 1/2, 27 over 16 is a relative max because now I did first derivative test. So I need to say g prime changes from positive to negative. That's why that is a relative max. Okay, so very important summary. This is sort of like we're going to be asked to whether various kinds of functions are increasing or decreasing. So it's really important to have the relationship between these things down. If a second derivative is positive, what does that tell me? If a second derivative is positive, it means that the derivative before that was increasing. And if the derivative of something is increasing, that means that you have a concave up function. So if you know concave up, then you know f prime is increasing, you know f double prime is positive, vice versa. You can go up and down. If you know f is, let's go this way. If you know f is concave down, that means you know that the first derivative is decreasing. And that also means that you know that the second derivative must be negative. And this works with, the fifth derivative, sixth derivative, seventh derivative, any three consecutive functions like that, derivatives, this relationship holds. All right, that's it for the notes today. Please come into office hours if you have any questions.